Okay, so in the last video, we talked about the first part of 14.2, basically how to work with two-way tables. And the big thing to remember is that the conditional distributions are inside the table. But the most important thing to remember with two-way tables is that the explanatory variable is the column variable, the response variable is the row variable. And the formula that we learned was to find the expected counts. It's row total times column total divided by total or table total. Okay, then the other formula that we learned that you need to have in your notes is the formula for the chi-square test statistic, which I cleaned that up a little bit here so it's easier to read. So chi-squared, okay, is equal to sigma. This capital sigma is the summation sign. So sigma of, or the sum of each one of these components. So observed minus expected quantity squared over expected. So obviously, when you have a two-way table of data, the first thing you want to do is that two-way table is going to give you all of these observed values, observed counts. You want to then fill in next to it, what are all the expected counts? Okay, right in the cells, in the conditional set, like inside. Okay, and then you want to figure out like each one of these components. Okay, so that's the long way of doing this. So now let's get more to the tests, the test for homogeneity, and then the test for association. Okay. So here's our example again of the type of music that's being played and then the type of wine that consumers are purchasing. Okay, so the null and alternative hypothesis. The null hypothesis is there's no difference in the distributions of wine purchases at the store. Alternative, there is a difference. Okay, and I'll show you how to write these. Okay, sorry, that's my dog. He's a little growly today. So we're going to proceed with caution because although the random and large sample size conditions are met, we aren't sure that individual observations are independent of one another, right? So our calculated test statistic was chi-squared equals 18.28. Now, just looking at this one number, 18 is a pretty large chi-squared, okay? So remember, the larger chi-square gets, the more evidence we have against the null hypothesis. And in this case, the null hypothesis is a statement of no difference or of homogeneity, like there's no difference. It's completely homogeneous. There's homogeneity between all the different types of wine being purchased, regardless of the type of music, right? So, but when we calculate this chi-squared and we get a value that's like, and generally a large chi-square would be, if you're in double digits for your chi-squared, that's a pretty darn big chi-squared. Okay, so that's probably going to end up giving you a very small p-value, something where you're probably going to end up rejecting the null. Okay, the DF that we use is the row minus 1 times the column minus 1, okay, which is equal to 4. Okay, so you're going to look in the DF equals 4 row if you're using table D. Actually, in our book, it's called table D. Okay, and we don't have an 18.28. We have 16.42 and 18.47. So this 18.28 is going to be pretty close to this value. Okay, a little bit larger than this p-value. Okay, but you can see that this is 0.001. So 1/10 of 1%. So that's a minuscule p-value. Okay, so we know that we're probably going to reject the null. So that means that the distribution is not homogeneous. That means that, you know what, people do get influenced by the type of music that's being played. Okay. Okay. So here we have a different example. Sorry, hang on one second. Okay, so in this example, what we're looking at is we are looking at, what are we looking at? Looks like cell phone usage, right? So cell only telephone use, or yeah, who is only using this? So remember this, even this fourth edition of the textbook is still pretty old. This is what, 2010, I believe. So this is still like 11 years old. So this is talking about, well, hey, who only has the cell only, or sorry, anyways, random digit dialing telephone surveys used to exclude cell phone numbers. Okay, not anymore. We know that we get junk calls, marketing calls on our cell phones all the time now. if the opinions of people who have only cell phones differ from those of people who have landline service, and I don't even know, I'm sure, hopefully, you guys all know what landline service is, but it's like the telephones that were actually like connected to telephone wires that actually run underground or over, well, anyways, landline service. The poll results may not represent, okay, may not represent the entire adult population. Okay, so the Pew Research Center interviewed separate random samples of cell only and landline telephone users who are less than 30 years old. So that's young people. Here's what the Pew survey found about how these people describe their political party affiliation. Okay, so we have these two populations, right? Cell only and landline only. Okay, we have two samples, right? So this is telling you that's the first clue that this is okay because there's two different populations that are being compared and two different samples. Okay, this is your clue that this is a test of homogeneity, not a test of association. Okay, which I haven't taught you yet, but with the test of association, you're not going to have two different populations. You're just going to have one population. Okay. All right. So here is the raw data or the observations. Okay. Here is what that looks like visually in a segmented bar graph, side by side segmented bar graph. So here's the cell only, here's the landline. Note that you have to have with segmented bar graphs, this is a throwback to chapter 1. You have to have a little key here or a legend which describes like what these different segments represent. Okay. But there is your data. So when you have data like this in a two-way table, the first thing you're going to do is get the totals, right? So we're given the column totals, but we need the row totals as well and the total. So what is our test? Okay, so state H null and HA. So there's no difference in the distribution of party affiliation in the cell only and landline populations. HA, there is a difference in the distribution of party affiliation in the cell only and landline populations. And again, we're going to use an alpha level of 0.05. Okay. Now, the only thing that this is missing is, well, there's no mu or p or anything like this. Okay. So we're using words here. Okay. If we have a p, okay, if we have proportions, then we have to define those parameters. But in this case, we're just using words. Okay. So what's the plan? The plan is if the conditions are met, we should conduct a chi-square test for homogeneity. Okay. Now, on the AP exam, you can just call this a chi-square test. You don't necessarily have to state whether it's a Goff, a homogeneity, or an association. Okay, you do have to name the procedure, but technically, you can just call it a chi-square test. Okay. Random, independent, and large enough sample size or expected counts. Okay, random, the data came from separate random samples of 96 cell only and 104 landline users. Large sample size, I'm going to call this expected counts condition. Okay, same thing, you can call it either one, it doesn't matter. Okay, we followed the steps in the technology corner, 705, to get the expected counts. The calculator screenshot confirms all expected counts are greater than or equal to 5. Okay, so here is all your expected counts. Now, how did we do this in the technology corner? Like, how did we do this? Well, this turns out this is super cool. When you make a matrix, okay, of the observations, when you make a matrix of these observations and you run a stat test, chi-square test, it will then actually create a corresponding matrix in matrix B, assuming you used matrix A for the observed counts. It will automatically fill in a matrix with all of your expected counts. Boom, awesome. Okay, very cool. Okay, but what was the formula to compute these by hand? How do you get these by hand? Okay, how do you get the expected counts by hand? That's something you have to know. How do you get the expected counts by hand? Who remembers? All right, so to get the expected counts by hand, it's row total times column total divided by total. Okay, so to get each one of these, okay, row total times column total divided by total. Okay, that's how you get the expected counts. Okay. The independent condition. Researchers took independent samples of cell-only and landline phone users, sampling without replacement used, so there need to be at least 960 cell-only users under age 30 and at least 10,000 or 1,040 landline users under the age of 30. This is safe to assume. Now, notice how there's two different things in independent. That's what I've been teaching you for the last couple chapters, right? Okay, because not only does there have to be independence like between the two populations, so that's what this first sentence is saying, but there also has to be independence within each one of those populations. And so since that we don't know, that's where we use the 10% condition. Okay. So with independence, some of you got a little bit sloppy and you kind of shortcutted this, and you're not going to get full credit on the AP exam if you shortcut this. You have to check, in this case, because you have two populations, you have to check really three things, right? So independence between the two populations, which is the first sentence, and then independence within each of the two populations, which is this second sentence, okay, which is the 10% condition, okay? So again, three conditions: random, expected counts, or we can call that large sample size, it doesn't matter. So random, expected counts or large sample size, and independence. Okay, you have to check those three. Our textbook only checks this. That is not correct. You will definitely lose points. I looked at the rubric for this year's AP exam, and they definitely want random and independence checked as conditions for chi-square. The do. So what do you need to include for the do? You need to include this: the generalized formula for the chi-square test statistic. Chi-square is equal to sigma times observed minus expected quantity squared divided by expected. You must have this generalized formula. You must have this secondary step. Okay. Now, notice that they have dot, dot, dot. You are allowed to have dot, dot, dot. Okay. This is the first component, the second component, and the last component. Okay, the first, second, and last component. Then there's dot, dot, dot for everything in between. Why? Because you're not actually doing this calculation. Okay, you're just using stat tests and then chi-square test, right? Okay, so you're actually not calculating each one of the components. Okay, and then your total, your summation of all of these, the sigma of all of these is 3.22. Now, just looking at that number, 3.22, that is a very small chi-square test statistic, right? What did I tell you? Generally, like if you have double digits, if you have 10 or greater, that's a very high chi-square. But 3, that's a pretty low chi-square. That's almost as low as you can get, right? In fact, what would be the lowest chi-square? Well, if you had a 0 chi-square test statistic, what does that mean? That means that your observed is exactly equal to the expected distribution. Okay, so using your calculator, your p-value is 0.20. So small test or small test statistics, small chi-square means pretty big p-value, right? So 0.20, that's a big p-value. You're not going to be able to reject the null. Okay. Our conclusion is the exact same conclusion I've been teaching you all year. It's 2 sentences. First sentence is about H null, whether you reject it or fail to reject it. You have to restate the p-value, compare it, okay, greater than or less than, to the restated alpha level. You have to have this in sentence 1. In sentence 2, you want to go ahead and talk about HA in context, okay? Again, I just checked the rubric for the AP exam. This is exactly what you have to have for your conclusion, okay? Now your follow-up analysis. Now in this case, we don't need any FUA. We don't need any follow-up analysis because why? We don't have statistically significant results. You only do a FU analysis when you have statistically significant results. By the way, is the question prompt going to ask you for a follow-up analysis? No, it never will. But do they expect you to do an FU analysis if the results are statistically significant? Yes, you must do the FU analysis. That is like step 5. Instead of a 4-step procedure, now you're going to have a 5-step procedure if you have significant results. Okay. In this case, p-value is high. We're not going to reject. We're going to fail to reject, so we're not going to do an FU. Okay. But here is what an FU is, okay? An FU, all you have to do is look at each one of the components, okay? What's a component? You got to know what a component is. Each one of these is a component, 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 component. Okay, so you have to look at all of the components, okay? And those components contribute to the test statistic, right? Because each one of these components added together sums up to the overall test statistic. So you look at which one of these components has the greatest contribution to the chi-square test statistic. In other words, which one of these values is the greatest value? Excuse me, sorry about that, is the greatest value. Now, if you have Minitab output, like I said, Minitab output is awesome because everything you need is right here. They even have it as the table, as the two-way table, right? Here's no music, here's French music, here's Italian music, then here is French wine, Italian wine, and other wine, right? And it has, look at each, what in the cell, what does it have? Oh my God, it has everything. It has the observed count, the expected count, and it has the contribution, right? It has the component right there, which is observed minus expected quantity squared divided by expected. It has the deviation right there, right? So again, observed count, expected count, standard deviation, okay, or component, I should say, right? Contributor. Okay, it even has the row totals and the column totals and the total. And right down here, what do we have? Check that out. It has the chi-square test statistic, 18.279. It has your DF that was used, okay, 4. And how did you get 4? 3 minus 1 times 3 minus 1. Okay, number of rows minus 1 times number of columns minus 1. 3 minus 1 times 3 minus 1. So 2 times 2 is equal to 4. Okay, so DF equals 4. P-value, 0.001. Okay, so in our music versus wine, okay, we had a very large chi-square test statistic, 18.279, which leads to a very, very small p-value, 0.001. Okay, Minitab output is awesome. Oh, I forgot to say what the follow-up analysis is. So look at all the contributions or components that contribute to the chi-square. So 0.52, that didn't contribute much. That contributed almost nothing. That contributed very little. That contributed literally nothing. Okay, here are the two biggest contributors: 7.62, 7.672, and 6.404. So you would talk about these two things being very unusual. Okay, so in your analysis, you would say, well, this one contributed the most. So what is this one? What am I talking about? Well, when French music is playing, the number 2 is Italian bottles of wine. The number of Italian bottles of wine sales went all the way down to just one bottle. So it seems like when French music is playing, people don't think about buying Italian wine. But when Italian music is playing, holy cow, 19 bottles of Italian wine, right? So Italian music playing seems to influence buyers to buy more Italian wine. Interesting. Okay, so that's your follow-up analysis. Okay, there's a good caution. Okay, here's a common student error. Many students incorrectly state HA as all the proportions are different. Okay? That is not what HA is going to be. HA is going to be at least, okay, one of the proportions is different. Okay, so in chi-square test for homogeneity, it allows us to test H null P1 equals P2 equals P3 equals P4 all the way to PK. This null hypothesis says that there is no difference in the proportions of successes for the K populations or treatments. The alternative hypothesis is that at least 2 of the PIs are different. Well, why is it 2 and not 1? Because in Goff, you only had 1 different. Well, because if 1 is different, then 2, you're comparing one to another, so obviously 2 of them are different. Okay, so there's 1 difference, but it affects 2 proportions. Okay, so remember I told you, I'll tell you how to write the null hypothesis. This is how you're going to write the null hypothesis for the chi-square test of homogeneity. Okay, you're not going to write it out in words. Okay, you're going to write it out in symbols, and then go ahead and define what each one of these parameters is, just like you did for the chi-square Goff. Okay. Okay, so here's an example. Say cocaine addicts need cocaine to feel any pleasure, so perhaps giving them an antidepressant drug will help. A 3-year study with 72 chronic cocaine users compared an antidepressant drug called desipramine, something like that, with lithium, standard drug to treat cocaine addiction, and a placebo. Okay, 1/3 of the subjects were randomly assigned to receive each treatment. Here are the results. Okay, so here's your two-way table. Okay, so with cocaine, relapse, okay, yes or no. Okay, treatments, desipramine, lithium, and placebo. Okay, so we want to perform a test of, okay, here is how you're going to write your hypotheses. Okay, P1 equals P2 equals P3. Your alternative is at least two of the PIs are different. Okay, because again, one difference means that two of them are different from each other. Okay, this is what these hypotheses mean in words. But again, you're going to write your hypotheses like this. Okay, and then define what your PIs are, where PI is equal to the actual proportion of chronic cocaine users, like the ones in this experiment who had relapsed under treatment I. Okay, and then we will use alpha equals 0.01. Okay. Plan, if the conditions are met, we should conduct a chi-square test of homogeneity. Again, you can just call this just the chi-square test if you want. Okay. Random, the subjects were randomly assigned to the treatment groups. Large sample size, again, I call that expected counts. Okay, you have to check that all the expected counts are greater than or equal to 5. Now, in our textbook, in our antiquated, outdated textbook, it says something about, oh yeah, well, if all of them are 5, but less than 20% of them are at least 1, then you're okay. No, forget that. They all have to be 5 or greater. Okay. All the expected counts are greater than or equal to 5, so the condition is met. Independent. The random assignment helps create 3 independent groups. If the experiment is conducted properly, then knowing one subject's relapse status should give us no information about another subject's outcome, so individual observations are independent. Okay, for the do, okay, you have to show the formula for the chi-square test statistic. Chi-square is equal to sigma observed minus expected quantity squared divided by expected, okay, which is equal to, there is your actual chi-square. We use the calculator, okay, to calculate that, okay. Using the DF equals 2, the calculator gives us a p-value of 0.0052. Again, very, very small p-value. Okay, again, big chi-squared. Remember we said double-digit chi-squareds. That's a pretty big chi-square. So 10.5, that's a big chi-square. Small p-value. Again, lots of evidence against the null. We're probably going to reject this null. Because the p-value of 0.0052 is less than alpha equals 0.01, we reject H null. We have sufficient evidence to conclude that the true relapse rates for the 3 treatments are not all the same. So another common situation, now we're going to switch gears and we're going to look at within one population. Okay, another common situation that leads to a two-way table is when a single random sample of individuals is chosen from a single population. There's your key. There's your clue that this is no longer homogeneity. You're not comparing 2 different populations and saying, hey, do they have the same distribution? Okay, that's homogeneity. Now you're looking within one population and you're looking at this distribution. And so this is a test of association. Okay, is there an association? Okay. That's what this test is called. All right, so a study followed a random sample of 8474 people with normal blood pressure for about 4 years. Okay, all the individuals were free of heart disease at the beginning of the study. Each person took the Spielberger Trait Anger Scale test. Okay, interesting name, pretty cool name. Anything that has the word anger in it, I don't know, I think that's pretty cool. Which measures how prone a person is to sudden anger. Ooh, I would probably be pretty high on this. I have a lot of sudden anger. Whoa, see, I'm real mad. No, just kidding. Researchers also recorded whether each individual developed coronary heart disease, CHD. This includes people who had heart attacks and those who needed medical treatment for heart disease. So there's your clue right there. We want to know, like already immediately just reading this context, you're trying to figure out, hey, is there an association between people who have sudden anger or people who score high on the Spielberger trait anger scale test and coronary heart disease? Like intuitively, we would think, well, yeah, I mean, people who have more anger would probably have more heart disease. That's what we would think, right? We would think there's a positive association, right? So this includes people who had heart attacks and those who needed medical treatment for heart disease. Here's a two-way table that summarizes the data. So here we have low anger, moderate anger, and high anger. Again, those are your that's your explanatory variable. CHD is coronary heart disease, no CHD. So it's either yes or no for CHD. Then there's your totals, okay, your row totals and your column totals, and you have your total, which is 8474. Okay. So what are you going to do with these? What are you going to do with these numbers? What did we learn in video one? Well, we're going to go ahead and figure out, well, what are the expected counts, right? So here are, what are we going to do? So we're interested in whether angrier people tend to get heart disease more often. That's what we sneakingly suspect. We suspect there's a positive association. Okay, we can compare the percents of people who did and did not get heart disease in each of the three anger categories. So go ahead and just figure out the 53 over 3110, okay, and 3057, okay, over 3110, then 110 over 47. So we're figuring out the marginal distribution, or excuse me, the conditional distributions. You can go ahead and graph them. Hey, there's a clear trend. Okay, as the anger score increases, so does the percent of people that suffer the heart disease. Okay, a much higher percent of people in the high anger category developed CHD than in the moderate and low categories, right? So here is our test for association. The null is always going to be a statement of, remember how I taught you originally that the null is a statement of no difference? Well, in this case, the null is a statement of no association. There is no association. And then the alternative is going to be, yes, there is an association. Okay, there actually is an association between the two variables. Okay. Um, some people, like your brains, might work better with independence. So no association means yes independence. So you might want to write this as yes independence and no independence. That confuses the heck out of me. I just like to stick with the one way with the association. So I go with no association. Why do I go with no association? Because again, all of our hypothesis tests are a test of no difference, no difference, no difference, no difference. So it's easier for me to remember no association, right? Status quo, no association. Right? That's how I like to think of it. Okay. With this, you actually are going to use words. Okay. You're going to actually write out your null and alternative hypotheses like this. Okay. Okay, same thing. We're using the same chi-square test statistic. Okay, alternatively, this is acceptable on the AP exam. Please don't do this to me, though, because my brain doesn't work that way. I don't teach it this way. I think it's much better just to do it this way, just to stick with association. Okay, so let's forget about independence. Okay. Again, DF is rows minus 1 times columns minus 1. Okay, and then p-value is just the area under the distribution under the chi-square density curve to the right. That's always a right tail question. Okay. All right, so there's your observeds, there's your expecteds, right? Row total times column total divided by total. Okay, so we want to perform a test of, there it is, no association versus there is an association. Okay, do you have to define any parameters? No, you don't. Okay, because you're not using p or mu or anything like that, right? So we'll use an alpha level of 0.05. Okay, so there's your state. Plan, if conditions are met, we will perform a chi-square test, right? If conditions are met, we should conduct a chi-square test. Okay, random, independent, and expected counts. Okay, again, all expected counts have to be greater than or equal to 5. Okay, and you have to show these. Okay, you have to show these. Here, they had a table with all of these, so you can see that they're all greater than or equal to 5, right? Greater than 5, greater than 5, greater than 5, greater than 5, greater than 5. They're all greater than 5. Okay, if you don't have this table, or if you don't fill out a table like this, then you have to specifically show what the actual expected counts are. You have to show your expected counts somewhere. Okay, it's easiest to, I like to just put the expected counts right here next to the, I like to put slash 69.73 slash 106.08, and then I write slash expected. That's what I like to do. Okay. Okay, so there are your conditions. The do. Okay, what happens in the do? You have to calculate the chi-square test statistics. So show the generalized formula, show one or two of these components, like how you substitute in the values. Then it's perfectly fine to do a dot, dot, dot here. Okay, and then show us what the final value is, 16.077. 16, that's high. That's a big chi-square, going to lead to a low p-value, going to tell us we're probably going to have statistically significant results. Okay. Do you have to show the DF? Yes, you do. Do you have to show this calculation of the DF? No, you don't. You can simply get the DF from the table. Okay. But you have to know how to calculate the DF, because there might be a multiple choice question on that. Okay. Rows minus 1 times columns minus 1. Okay. So 2 minus 1 is 1, 3 minus 1 is 2, so 1 times 2 is 2. Okay. To find the p-value. Use your calculator to find the p-value. If you don't know how to use a calculator, or you're not using stat tests or whatever, you can simply use, once you have your chi-square test statistic, you can use chi-square CDF. Okay, then the parameters you're going to put in are, well, what is the actual chi-square? Okay, it's 16.077 calculated here. Okay, 1000, comma 2. Okay, there's your DF right there. Okay, and it'll give you your p-value, which is extremely tiny, 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 tiny. Conclude, it's the same conclusion that I've taught you like all along. Okay. Here's a couple of caveats. Okay, I'll let you read those on your own. This is how you tell the difference. Okay, those two check marks, those two red check marks. If the data come from 2 or more independent random samples or treatment groups in a randomized experience, then it's homogeneity, because you're comparing 2 groups, right? So that's homogeneity. Okay. If the data come from a single random sample with the individuals classified according to 2 categorical variables, use a chi-square test for association. Now we're trying to see, is there an association or is there no association, right, between the 2 variables? Definitely want to have both of these formulas written in your notes. Expected counts is row total times column total. That's a times. Row total times column total divided by total total. They call it table total, but I call it total total. This would be chi-square is equal to sigma, capital sigma, which is the summation sign. So chi-squared is equal to sigma, observed minus expected, quantity squared divided by expected. Okay, so you need to know both of those, right? All right, guys, we're done. Guess what we get to do next chapter? We get to do more transformations. Yay, we love mathematical transformations. And we get to do inference for linear regression. Whoa, linear regression. We haven't done that in about, like 10 chapters, right? We haven't done linear regression in a long time, okay? So can you guess what your null hypothesis is going to be for inference for linear regression? Remember, so far, null hypothesis has been statement of no difference, statement of no association, statement of just status quo, right? So can you guess what this null hypothesis is? I bet you can't. I couldn't, but we'll find out pretty soon. Thanks, guys. See you in the next video. Good luck on your next quiz.